Welcome! Today, we'll explore LeetCode problem number 592, fraction addition and subtraction. This problem challenges us to evaluate a mathematical expression containing fractions and return the result in its simplest form. Let's dive into the details and solve it step by step. In this problem, you're given a string that represents a mathematical expression involving fractions. These fractions are separated by either a plus or dash sign. Your goal is to evaluate the entire expression and return the result as a fraction in its simplest form, written as a/b, where a is the numerator and b is the denominator, with b always being positive. The input string is formatted such that each fraction appears as n/d, where both n and d are integers. Additionally, the fractions are combined using either addition or subtraction. The output should ensure that the numerator and denominator share no common divisors other than 1. If the result of the expression is negative, the negative sign should appear in front of the numerator. For example, consider the input expression -1/2 plus 1/2. When we evaluate this, the two fractions cancel each other out, resulting in 0. The output for this case should therefore be 0/1, where the fraction is expressed in its simplest form. Now, looking at another case, -1/2 plus 1/2 plus 1/3, the initial two fractions, -1/2 and +1/2, also cancel out, leaving just 1/3. Since 1/3 is already in its simplest form, the output is simply 1/3. These examples demonstrate how to handle both addition and subtraction while ensuring the result is expressed correctly. Another example to consider is the expression 1/3-1/2. Here, we need to subtract the two fractions. To do this, we first find a common denominator for 3 and 2, which is 6. Converting the fractions, 1/3 becomes 2/6, and 1/2 becomes 3/6. Subtracting these gives 2/6, 3/6, which equals -1/6. The final result is expressed as -1/6, ensuring that the fraction is in its simplest form and that the negative sign is correctly placed before the numerator. The constraints for the problem specify that the input string will always contain at least one fraction, and it will only include fractions in the form n/d combined with plus or dash operators. Both the numerator and denominator are integers, and the denominator is always greater than 0. The absolute values of the numerator and denominator do not exceed 10,000, meaning intermediate calculations could result in large values, so it's essential to handle these efficiently to avoid overflow. Additionally, if the result of the expression is 0, the output must be 0/1. The denominator in the output should always be positive, and special attention is needed to handle negative fractions correctly during addition or subtraction. By keeping these constraints and edge cases in mind, we can ensure that the solution is both correct and robust. To tackle the problem of fraction addition and subtraction, we need a strategy that parses the input string, performs arithmetic operations between the fractions, and reduces the result to its simplest form. One basic approach is the brute force method. Here, we break down the input expression into individual fractions and their associated signs. Each fraction is then converted into its numerator and denominator, and we add or subtract them step by step. To combine fractions, we calculate the least common denominator, perform the arithmetic on the numerators after adjusting them, and simplify the resulting fraction by dividing both numerator and denominator by their greatest common divisor. The brute force approach is straightforward and easy to grasp, but it involves a lot of repetitive calculations, especially for the least common denominator and greatest common divisor, which can make it inefficient for longer inputs. While the brute force method is simple, it has its limitations. On the positive side, it's easy to implement and understand, making it a good starting point. However, the repeated calculations of the least common denominator and greatest common divisor can quickly add up, especially for more complex or lengthy expressions, leading to inefficiencies. To address this, we turn to the optimized approach, which builds on the brute force idea but reduces redundant computations. The key improvement here is maintaining a cumulative numerator and denominator as we process the expression. Instead of recalculating the least common denominator for every pair of fractions, we compute it iteratively as we combine the fractions one by one. By simplifying the result only once at the end, we further streamline the process. This approach involves parsing the input into fractions and signs, initializing a starting fraction, and updating the cumulative result fraction by fraction. Finally, the resulting fraction is simplified and returned in its simplest form. The optimized approach offers a great balance between clarity and efficiency, but there are still other methods worth considering. For example, an alternative strategy involves directly parsing the input and delaying least common denominator calculations until the very end. In this method, instead of simplifying fractions after each operation, we keep track of all denominators and compute the overall least common denominator once the entire expression has been processed. This avoids intermediate simplifications, making the approach potentially simpler in terms of arithmetic. However, it comes with a trade-off: the need to store additional intermediate denominators, which can increase memory usage. While this method simplifies intermediate steps, its less intuitive nature and extra storage requirements make it a less appealing choice compared to the optimized approach. The optimized approach was selected because it strikes the right balance between efficiency and clarity. By maintaining a cumulative fraction and performing operations iteratively, we minimize redundant calculations, such as repeatedly finding the least common denominator. This makes the approach not only faster but also more scalable for longer expressions. A particularly insightful realization was that simplifying the result only once at the end eliminates unnecessary overhead during intermediate steps. Compared to the brute force method, this approach significantly reduces time complexity. Speaking of complexity, the time complexity is linear, or O(n), because parsing the input string and performing fraction operations scale with the length of the string. The space complexity is also O(n), as we need to store the parsed fractions. Overall, this strategy provides a structured and efficient way to handle the problem, making it the ideal choice for this task. To tackle the problem of adding and subtracting fractions from an input string, we break the solution into structured steps. First, we need to parse the input string, which contains fractions separated by plus or dash. These fractions are expressed in the format numerator/denominator. Using either a pointer or regular expressions, we can systematically extract these fractions along with their respective signs. For instance, the input -1/2 plus 1/3 would be parsed into a list like -1/2 plus 1/3. Next, we define a few helpful utility functions to simplify our calculations. These include GCD to find the greatest common divisor of two numbers, LCM to determine the least common multiple, and simplify_fraction to reduce fractions to their simplest form by dividing the numerator and denominator by their GCD. Lastly, we initialize an accumulated fraction starting at 0/1, which acts as our running total as we process each fraction in the input. Now, we process each fraction in the parsed list. For every fraction, we extract its numerator and denominator, then calculate the least common denominator, or LCD, between the current fraction's denominator and the denominator of the accumulated result. With this common denominator, we scale the numerators of both fractions to match the LCD. Depending on the sign of the fraction, we either add or subtract the numerators, updating the accumulated fraction accordingly. Once all fractions have been processed, we simplify the resulting fraction using the simplify_fraction function to ensure it is in its simplest form. It's important to verify that the final denominator is positive for correct formatting. Finally, we return the result as a string in the format numerator/denominator, which represents the evaluated expression. There are several key insights that make this approach both efficient and robust. First, understanding that adding or subtracting fractions requires a common denominator is crucial. This is why the least common multiple, or LCM, plays such a central role in our algorithm. Simplifying the fraction at the end ensures the result is presented in its simplest form, which is often a requirement in competitive programming. Special attention is also needed to handle the signs of fractions during addition and subtraction to avoid errors. Additionally, we must account for edge cases, such as inputs with only one fraction, negative fractions, or results with zero numerators. For instance, 3/4 simply outputs 3/4, while -1/2 plus 1/2 results in 0/1. Lastly, large inputs with multiple fractions are handled efficiently thanks to our structured algorithm. To store and manipulate data, we use lists for sequential processing of fractions and tuples to represent each fraction as a pair of numerator and denominator. The core operations in this problem include computing the greatest common divisor, GCD, and least common multiple, LCM. The GCD is essential for simplifying fractions, while the LCM allows us to calculate a common denominator for addition and subtraction. Simplification ensures that the fractions remain manageable and prevents overflow in intermediate calculations. Parsing is another critical step, as it guarantees accurate extraction of both the fractional components and their signs. From a complexity perspective, parsing the input string is linear in time, or O(n), where n is the length of the string. Processing each fraction, including GCD and LCM computations, has a logarithmic time complexity relative to the size of the numbers. For k fractions, this results in a total processing time of k*log max_denominator. Simplifying the final result adds an additional log max_denominator. Therefore, the overall time complexity is n plus k*log max_denominator, while the space complexity is k, as we store the parsed fractions in a list. To tackle the problem of fraction addition and subtraction, we start by importing the GCD function from Python's math module, which we'll use later for simplifying fractions. Then, we define our class solution and the method fraction addition that takes in the input expression, which is a string of fractions separated by plus or dash. Within this method, we first define a helper function, LCM, to calculate the least common multiple of two numbers. This will be important when aligning denominators for the addition of fractions. Next, we initialize an empty list called fractions to store individual fractions as tuples of numerators and denominators. We also set up a variable I to traverse the input string. As we iterate through the string, we check if the current character is a plus or dash, which helps us determine the sign of the fraction. If a sign is found, we adjust the sign variable accordingly and move to the next character. Then, we identify the numerator by marking its starting position and continuing until we encounter the / character. Once the numerator is extracted, we multiply it by the sign to account for positive or negative values. Similarly, we extract the denominator by moving past the / and reading consecutive digits. Each fraction, represented as a tuple of its numerator and denominator, is then appended to the fractions list. This process continues until the entire string is parsed. Once all the fractions are parsed, we initialize the result numerator as 0 and the result denominator as 1. These will hold the cumulative values as we process each fraction. To align all fractions to a common denominator, we iterate through the fractions list and update result_denominator using the least common multiple of the current denominator and the denominators of the fractions we've encountered so far. This ensures all fractions can be added together. Next, we calculate the adjusted numerators for each fraction. By iterating through the fractions list again, we scale each numerator to match the common denominator and accumulate their sum into result_numerator. At this point, we have the combined numerator and denominator for the result, but they may not be in their simplest form. To simplify, we compute the greatest common divisor of the absolute value of result_numerator and result_denominator, then divide both by this common divisor. Finally, the resulting fraction is returned in string format as numerator/denominator, representing the simplified sum or difference of the input fractions. Here, we start by importing the necessary Java utilities and defining our solution class. The main method we're working on is fraction addition, which takes a string expression representing a series of fractions to be added or subtracted. First, we initialize a list called fractions to store the parsed numerators and denominators, and an index variable I to iterate through the string. The goal is to parse the input expression into individual fractions. To handle signs, we check if the current character is a plus or dash and update the sign variable accordingly. Next, we parse the numerator by identifying its start position and reading until we encounter a /. Once we have the numerator, we multiply it by the sign to ensure its value reflects whether it's positive or negative. After processing the numerator, we increment the index to skip the / and repeat a similar process for the denominator, which we identify by reading the subsequent digits. These parsed values are then stored as an integer array in the fractions list. Once the loop completes and all fractions have been parsed, we move on to computing the result. We initialize result numerator to 0 and result denominator to 1. The next step is to find the least common multiple, or LCM, of all denominators. This is crucial for aligning the fractions to a common denominator for addition. We iterate through each fraction in the list, updating result denominator to the LCM of its current value in the fraction's denominator. After calculating the common denominator, we adjust the numerators of each fraction to match this common denominator and sum them up. This is done by scaling each numerator proportionally and adding it to result numerator. Finally, we simplify the resulting fraction by calculating the greatest common divisor, or GCD, of the absolute value of the numerator and the denominator. We divide both by the GCD to reduce the fraction to its simplest form. The result is then formatted as a string and returned, combining the simplified numerator and denominator with a / in between. To support the operations in the main method, we define two helper functions, GCD and LCM. The GCD function calculates the greatest common divisor of two integers using the Euclidean algorithm. This works by repeatedly taking the remainder of a divided by b until b becomes 0, at which point a holds the GCD. Next, the LCM function computes the least common multiple of two numbers. It leverages the relationship between GCD and LCM, which states that the product of two numbers is equal to the product of their GCD and LCM. By dividing the product of a and b by their GCD, we efficiently find the LCM. These utility methods ensure that our fraction addition algorithm is both efficient and modular, enabling precise computation of the final result. Here, we're working with the input string -1/2 + 1/2. The first step is to parse the expression into individual fractions. We start with an empty list called fractions and initialize the index I to 0. The first fraction, -1/2, is parsed by identifying the negative sign at the beginning, extracting the numerator as -1 and the denominator as 2. This gives us the fraction, -1, 2, which we append to the list. Next, we parse +1/2. The positive sign is identified at position 4, and we extract the numerator as 1 and the denominator as 2, resulting in the fraction, 1, 2. After appending this to the list, the fractions array contains -1, 2, 1, 2, and we're ready to move on to the next steps. Now that the fractions are parsed, we need to compute their least common denominator, or LCD. We initialize the result _denominator as 1 and iterate over the fractions. For the first fraction, -1, 2, the least common multiple of 1 and 2 is 2, so we update the result _denominator to 2. The second fraction, 1, 2, doesn't change the denominator since the LCM of 2 and 2 remains 2. With the LCD determined, we move to combining the numerators. Starting with result _numerator as 0, we adjust each numerator to match the common denominator. For -1, 2, we calculate -1 asterisk, 2 / 2 equals -1, updating result _numerator to -1. Then, for 1, 2, we add 1 asterisk, 2 / 2 equals 1, which brings result _numerator back to 0. This gives us the intermediate result 0/2. Finally, we simplify the fraction. The greatest common divisor of 0 and 2 is 2, so dividing through by 2 results in the simplified fraction 0/1. The output for this example is 0/1. For the input 1/3-1/6, we begin by parsing the expression into individual fractions. Starting with an empty fractions list and I at 0, we process the first fraction, 1/3. Since there's no sign at the beginning, the fraction is positive by default. We extract the numerator as 1 and the denominator as 3, giving us 1, 3, which we append to fractions. Next, we parse the second fraction, -1/6. The negative sign at position 4 indicates a sign of -1. We extract the numerator as -1 and the denominator as 6, resulting in -1, 6. Appending this to the list, we now have fractions equals 1, 3, -1, 6. With the fractions parsed, we can move on to the calculations. To solve the example, we calculate the least common denominator. We start with result _denominator as 1. For the first fraction, 1, 3, the LCM of 1 and 3 is 3, so we update result _denominator to 3. For the second fraction, -1, 6, the LCM of 3 and 6 is 6, updating the denominator to 6. Next, we combine the numerators. With result _numerator initialized to 0, we process 1, 3 first. The adjusted numerator is 1 asterisk, 6 //3 equals 2, so we update result underscore numerator to 2. Then, 4 minus 1, 6, we calculate dash 1 asterisk, 6 //6 equals dash 1, updating result underscore numerator to 1. This gives us the intermediate result 1/6. Finally, we simplify the fraction. The GCD of 1 and 6 is 1, so no further reduction is needed. The simplified result is 1/6, which is our final output. Given the input 5/3 plus 1/3, we first parse the expression into fractions. We initialize fractions as an empty list and start at index I equals 0. The first fraction, 5/3, is positive by default since no sign is present. The numerator is 5, and the denominator is 3, forming 5, 3, which we append to fractions. The second fraction, plus 1/3, has a positive sign at position 4. Extracting the numerator as 1 and the denominator as 3, we get 1, 3, and append it as well. At this point, fractions equals 5, 3, 1, 3, and we are ready to calculate the result. To solve this example, we first compute the least common denominator. Starting with result underscore denominator equals 1, we process 5, 3. The LCM of 1 and 3 is 3, so we update result underscore denominator to 3. 4, 1, 3, the LCM of 3 and 3 remains 3, so the denominator doesn't change. With the LCD determined, we proceed to combine the numerators. Starting with result underscore numerator equals 0, we process 5, 3, by calculating 5 asterisk, 3 //3 equals 5, updating result underscore numerator to 5. Then, 4, 1, 3, we calculate 1 asterisk, 3 //3 equals 1, updating result underscore numerator to 6. This gives the intermediate result 6/3. For simplification, we find the GCD of 6 and 3, which is 3. Dividing through by 3, the numerator becomes 2 and the denominator becomes 1, resulting in the simplified fraction 2/1. The final output for this example is 2:1. To analyze the time complexity of the solution, we can break it down into several key steps. First, we have the parsing of the input expression. Here, the algorithm scans through the input string to extract the numerators and denominators of each fraction. Since it processes each character of the string once, this step has a time complexity of O(n), where n is the length of the input string. Next, we compute the least common multiple, or LCM, of the denominators. For each pair of denominators, we use the GCD function, which operates in O, log, min, A, B, time for inputs at NB. If there are k fractions in the input, calculating the LCM iteratively for all denominators results in a complexity of O, k asterisk log, max underscore denominator, where max underscore denominator is the largest denominator among the fractions. Finally, we adjust the numerators to align with the common denominator. This step involves performing k multiplications and additions, making its time complexity O, k. After adjusting the numerators, we need to simplify the final fraction. This involves calculating the GCD of the numerator and denominator for the resulting fraction. Since the GCD computation operates in O, log, min, abs, result underscore numerator, result underscore denominator, this is the time complexity for this step. When we consider all the steps together, the overall time complexity is dominated by the parsing operation and the iterative LCM computations. By combining these, the total complexity can be approximated as O, n plus k asterisk log, d, where d represents the maximum value of the denominators or numerators. Now, for the space complexity, the input string expression is stored in memory, which requires O, n, space. Additionally, we store the fractions in a list, where each fraction is represented as a tuple of numerator and denominator. Since there are k fractions, this step requires O, k, space. Beyond the input storage and the list of fractions, we also use a few intermediate variables like result underscore numerator, result underscore denominator, and temporary variables during the parsing and computation steps. These variables occupy constant space, so their contribution to the overall space complexity is O(1). When we combine all the space requirements, the total space complexity becomes O(n plus k). This optimized approach is much more efficient than a naive method, where we might multiply all denominators together and directly perform additions and subtractions without simplifying intermediate results. Such a naive approach could lead to very large intermediate values, making the calculations computationally expensive. By leveraging LCM and GCD optimizations, this solution avoids unnecessary overhead and ensures that we work with manageable numbers throughout the process. Looking at specific scenarios, the best case performance occurs when all the denominators in the input are already the same. In this case, the LCM computation becomes trivial and can be completed in constant time, reducing the overall complexity to O, n plus k. For the average and worst case scenarios, where the denominators are diverse and potentially large, the complexity remains O, n plus k asterisk log, d, as determined by the LCM and GCD computations. To provide a mathematical justification for this big O bound, we note that the parsing step contributes O, n, and the LCM computation contributes O, k asterisk log, d. Since the LCM step iterates through all fractions and performs logarithmic GCD operations for each, these are the dominant factors. Constants, such as those from multiplications or additions, do not affect the asymptotic complexity, confirming that this bound is both tight and accurate. When solving fraction addition and subtraction problems, there are several common mistakes to watch out for. First, incorrect handling of negative signs is a frequent issue. For instance, in the expression -1/2 plus 1/3, it's essential to associate the negative sign with the numerator of the first fraction during parsing. Misplacing it could lead to entirely wrong results. Next, failing to reduce the resulting fraction to its simplest form is another common error. After performing arithmetic operations, the result should be simplified using the greatest common divisor, or GCD, to ensure accuracy. Another pitfall is mishandling mixed input formats. Some inputs may omit explicit plus signs or include inconsistent spacing, such as 1/3-2/3. If you don't account for these variations, parsing errors can occur. Additionally, a common misstep is using division instead of multiplication when calculating the least common multiple, or LCM, of denominators while aligning fractions. Finally, for larger inputs, failing to simplify fractions at intermediate steps can lead to overflow errors. Using tools like Python's math.gcd can help prevent these issues by ensuring calculations remain manageable. Now, let's discuss some insights that are particularly relevant during interviews. Effective string parsing is a critical skill, and interviewers will often test your ability to handle edge cases, such as missing signs, extra spaces, or improper fractions. Demonstrating a clear understanding of mathematical concepts like GCD and LCM, and showing you can compute them efficiently, is another highlight. Structuring your solution into modular functions is also important. For example, breaking the problem into separate components for parsing, intermediate calculations, and fraction reduction not only makes your code cleaner but also showcases your systematic approach to problem solving. Furthermore, you should be ready to discuss the time complexity of your solution. Parsing the input string typically has O, n, complexity, while finding the GCD operates logarithmically relative to the size of the numbers. Arithmetic operations like multiplication and addition are generally constant for smaller inputs but can scale with larger numerators and denominators. Lastly, exploring similar problems can deepen your understanding. For example, LeetCode 224 and 227 involve evaluating arithmetic expressions, while problems like 66 and 150 focus on arithmetic operations in different contexts. These related challenges can help you refine your approach to fraction addition and subtraction. Finally, let's consider some alternative approaches for solving this problem. One option is brute force parsing, where you manually extract numerators and denominators by iterating through the input string character by character. While this approach is straightforward, it's prone to errors, especially with edge cases, and can be tedious to implement. Another method is using regular expressions to extract all fractions and their signs from the string. This can make parsing cleaner, but regex can be slower for longer strings and harder to debug. A more streamlined option is leveraging Python's fractions fraction class, which handles fraction arithmetic and automatic reduction for you. This approach is fast and reduces the risk of errors, but it may not showcase lower-level problem-solving skills, which are often critical in interviews. Alternatively, you can write custom functions to handle fraction arithmetic manually, including calculating GCD, LCM, and performing addition and subtraction. While this requires more effort and introduces additional complexity, it demonstrates a solid grasp of mathematical concepts and algorithm design. Each approach has its own trade-offs, so choose the one that best aligns with your goals and the specific requirements of the scenario. Great work! We reviewed how to solve the problem by parsing fractions, finding common denominators, and simplifying results. Remember to practice similar problems to strengthen your skills. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!